All right, so a lot of basic information on here that you probably are aware of if you're here, like the fact that it's the co-class and the class meetings are now Tuesday, Thursday from 2 to 4. Office hours are Monday, Wednesday, Friday, 9 to 10 and 2 to 3. Tuesday, Thursday, 11 to 12, although I didn't have it today, just not the first few minutes. So I should be holding them regularly from now on. Monday and Tuesday, not as much because I was doing other things. Next week, I do have, I'm interviewing someone, so a few of my office hours will be canceled. I will post an announcement about that to make sure you don't try and show up while I'm not here. The password for the Zoom meetings is Newton. You may or may not have actually had to enter it. Fine if you didn't have to. Although I'm supposed to have it. Yeah. You might not have had to enter it if you're like already logged in with SSO or something. I don't actually know. There's my name, call me James. There's my email address. Email is usually the best way to get a hold of me. Although I will say, if you're trying to get a hold of me specifically for a math question, like, hey, James, how would I start this problem? Although you're welcome to email me, I would really, really, really encourage everybody to, instead of emailing me your math questions, try starting a discussion in Canvas. So you go here. Oh, look, I already have a few discussions going. So like if you could even, you could go into the do you have any questions one, and you could write, hey, James. You don't have to write, hey, James, but you can just, for example, you could write, hey, James, how do I find the typos abound, the antiderivative of, and then you can do cool math stuff. You don't have to do math stuff. But so here's one thing I'll say. The reason this is great, as opposed to emailing me, is in Canvas, I can write with math type, meaning that I can write an answer that's gonna, or a suggestion or whatever, that's gonna look a lot nicer and be easier to read. So while I will definitely take your emails, I might actually respond to them as a discussion, but really, 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 I would encourage everybody to, if you have math questions that you want to see kind of laid out step by step, I will usually answer them, or your classmates can also answer them here. But if you do it here, I will probably answer it relatively rapidly. I will write it nicely, and everyone can see it. And also other people can chime in too. So if someone else has an answer before, I can be like, hey, great. But right, we could do something like this, and then I forget what the little math button is. I think it's over here. Yeah, there we go. How do I find the antiderivative of? I prefer the advanced view. F of x equal to, I don't know, secant squared of x plus tangent squared of x, for example. So then it looks all nice and mathy, right? So that's just something to be aware of. Cool. So I would really, 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 as you might have guessed, encourage everybody to, if you have math questions that you like, not during obviously class or right outside of class or office hours, you're like, hey, I need help with this thing. This is really a great place to try and get that help. Whenever you post a discussion, I get an email notification, and I see my email on my phone all the time. So I'm usually pretty likely to respond, as long as I'm not like sleeping around in the world doing stuff. I'm usually pretty likely to respond fairly rapidly. All right, let's go back to the home syllabus stuff. So there's my email. Email is great for not math questions. Discussions are great for math questions. And then if you have some sort of math emergency, you can always call me or text me. But really, this was more for when I was teaching a class and I was giving exams. Like last quarter, I was teaching a pre-16 class, and my students actually had exams given by me. And occasionally there were some technology issues where they weren't able to upload stuff right away. That was more for them, but I left it on for these ones. So if you have something that's really, really, really urgent, you are welcome to call or text me, but I can't imagine there will be anything super urgent for this class. So you're probably best off just emailing me, because also emails on my phone, I see it right away. It's just as good as a text message, really. All right, let's talk about the details of the class. Oops, sorry, let's scroll a little too fast there. So some notes about co-class. This course is meant as a support class for students who are concurrently enrolled in Math UNB, which you all should be. Each class period will consist of me showing you examples and demonstrating how to solve them, maybe asking you to do work on occasion, although typically that's more of an in-person kind of deal where I'm like, hey, work on this problem, then I'll walk around and look at it. Can't really do that here. So most of the time, it'll probably be me demonstrating something. Occasionally, I might have you guys work on something for a minute or two, type your answer in the chat or something like that. Also, I would encourage everyone, I'm getting the text message. Oh, I forgot to have to, oh no, that's fine, I'm good. I would encourage everyone to familiarize yourself, as I imagine. So imagine everybody at this point, right? We're in like the fourth quarter of online Zoom university. I imagine everyone's fairly familiar with Zoom. I would encourage you to familiarize yourself with the, oh gosh, I can't, of course, I can't see them when I'm sharing my screen, the reactions. So, right, oh, look, there's a laughing, crying face now. Okay, joy, I got some joy going on. So occasionally I might ask you guys a question that's like a yes or no answer, and you can just answer with a yes or a no. White, green check is yes, red check no. And I think they are persistent now. There was an update for a while where they went away. Like they would stay there for like 10 seconds and then go away. But I think they just persist now. So you do have to like kind of turn them off, I believe. Yeah, you do. So also, if you don't like if you want to say words, but you don't want to just interrupt, it's really okay if you interrupt. But if you don't feel like that, you can also use the raise hand reaction. And once I see it, I will definitely call on you and prompt you to speak. I should lower my hand. That's lame. Interesting. I wish the little box for the reactions would stay up, but you have to like open it every time you want to click on a reaction, at least as far as I can tell. All right, anyway. I will record, edit, and post the class sessions afterwards so that you can view them. That also goes hand in hand with the absence policy down here, which we'll talk about in a second. Yeah, this down here. Oh, yeah, okay. Keep getting texts. Who is texting me? That was a voicemail. All right, no big deal. So this class is graded pass, no pass. Passing grade is 75% or higher. 50% of your grade will be based on your attendance. So if you're here, you get credit for being here. I will take attendance for everybody. Even if you're not actually enrolled in the class, I'm still going to take your attendance because we count the students that we serve and we enter into some database. So that's why I'll be collecting I usually take a screenshot of who's in class and then go mark your attendance in Canvas. And then at the end of the quarter, download it all and enter it into some other system. So if you're here, I will definitely mark that you are here. 25% of the class grade will be based on your completion of the weekly reflections, which we will talk about in a moment. As long as you do it, you will get credit for doing it. And then likewise, 25% of the class grade will be based on completing the weekly quizzes. Quiz grades are based solely on whether or not you complete the quiz, meaning that as long as you earnestly try to, right, as long as you turn something in that isn't just like a blank piece of paper, you'll get credit for doing the quiz. It's not hard to pass this class. Right, it's 1 unit of workload credit. The intention is that everybody passes as long as you do the things you need to do to pass. That said, if you don't pass, it's also not the end of the world. Right? If you didn't do the things and you didn't pass the class, the only time it would be kind of a big deal is if this was like the 12th unit you have, right, to make sure that you're meeting the minimum progress. Other than that, not passing this class is really not a big deal. That said, everybody can and should pass as long as you come, which is kind of right. Why do you sign up if you're not going to come? So I should say, so as far as the quizzes go, they'll be weekly. I will post them, and then you should all do them. I will definitely grade them, and I'll grade them in Gradescope, and I'll write comments in Gradescope. So what I'm trying to say the longest way possible is you should look at Gradescope after I've graded your quizzes, because there will be feedback there about what you've done right and what you've not done right. So you'll still get full credit. So if you're just looking like, oh, I got 100%, that's meaningless as far as what you actually got right or wrong. So you actually have to go in Gradescope and look at what I've written to see. And maybe next week, next week after we've had some quizzes turned in, maybe I'll show you guys all what I mean exactly by that, but I don't think it should be too terrible. As far as absences, you can make up a maximum of 10 absences, which is, I think, like half the class meetings, just by watching the video of the class you missed the same week that you missed it. So like if you missed class on Thursday, I would ideally before the next class is probably the best way to do it. But yeah, watch the class within a week and then email me as soon as you've watched it to let me know to update the attendance. I do need you to email me the same week you watched it, because I don't want at the end of the quarter 10 different people saying, James, I watched all these classes and mark me here. No, it's got to be each week. Tell me if you're missing class. Hopefully you don't miss that many classes. We don't have to deal with it. Not a big deal. But obviously, right, we're in a world where people are watching things on their own schedule, which is perfectly fine. I'm happy for people to get the information in any way, shape, or form. So if you're not able to attend class live, which I definitely understand, you can watch the videos and you can get credit for being here. I will also say, if you're not enrolled in the class, but you're still watching the video later, I would appreciate you letting me know so that I can still count you as having attended, because again, we keep track of the students we serve, and the more students we serve, the better our funding outlook looks in some ways. So do let me know if you're watching the videos and not coming to class. Perfectly fine, just let me know. As far as this class goes, this class, Code 21B, is worth 1 workload unit. Doesn't count towards graduation, but it does count towards being full-time status as far as minimum progress and financial aid and visa. Again, down here, a plug for the discussion, so you can use the discussion tab, right? It's right over here in Canvas to converse with each other, right? You can ask questions. I will frequently chime in if you ask questions in discussion, but the rest of you can also talk to each other that way. I know there's lots of ways to communicate with each other, like Discord, like other things. I forget there was something else, like something me. I don't remember what it is, but I heard about it. So yeah. Some notes about the class. This stuff is more just kind of the usual. Each unit in the course is connected to the other stuff. Yeah, right. You gotta learn how to do derivatives before you can do antiderivatives, and you gotta learn some, right. The things build upon each other is what this whole paragraph is saying. And you got to make sure you understand the previous stuff before we get to the next stuff. So I would say 21B is probably, in some sense, one of the harder calculus classes, in my opinion. I did take 21B many years ago at UC Davis. Gosh, many years ago. I think I took it I don't want to date myself here, but I think I took it in 1999. Okay. Yeah, I took it in 1999 with Dr. Marks. It was a great class. It was really hard. I mean, I got an A, but it was really hard. Did I get? Yeah. But what I want to say is what makes 21B hard is that there's lots of methods of integration. And unlike differentiation, where you're taking, have this Discord thing keeps making noise. Go away, Discord thing. I guess I can just close you. Yeah, fine. Okay, sorry. What makes 21B hard is that, unlike differentiation, where it's usually pretty clear what step to take, like you see things multiplied together, oh, use the product. When you see a function of a function, use the chain rule. With integration, it can be a lot less clear what method of integration we need to use. And sometimes it's a guessing game. There are kind of ways of narrowing down or seeing what we want to do. And actually, I've got a whole handout on that we'll kind of talk about as we go through the different methods of integration. But this class especially, I think, requires a lot of time and dedication. So be prepared to spend a lot of time studying this stuff, practicing this stuff, which is kind of what this next part says. Successful students usually spend 10 to 20 hours per week doing homework, practice problems, et cetera, et cetera. Get help as soon as you need it. I'm obviously here. Email, discussions. Discussions are better than email. You can also see me in office hours where we can just talk, and I will write things on my lovely whiteboard here. There was something else. No, I know. You can also make an individual appointment with me, which I will show you how to do that in a second. And then there's also other math specialists. So if you were in Code 21A last quarter with obviously not me, and you really like the person you were in Code 21A with, you are welcome to get, I imagine they probably would say, you are welcome to get in touch with Casey or Claire or Duff or Grant or Sarah and ask them for help with stuff. They have office hours too. We're all happy to help you guys, right? You can also get this sentence. Yeah, you can get help from a student tutor, an online drop-in, or a one-on-one appointment via this link. I don't think they're live quite yet, but they will be next week. Other places to get help, there's our website, there's Grant's website, which I'm not gonna lie, I use a lot. He's got great examples, especially the 21 series examples. Grant has lots of great stuff. He's got problems here. So for example, I'm literally looking at this one today, where I have it right over here. Here's code 28 problem solving 0. I'll probably pull some problems from here, or at least some inspiration from here. And then also their solutions. So if you're looking for extra practice, this is a great place to find it. I mean, I know you don't have enough homework to do already, but if you find yourself in need of more practice problems, this is a great place to look for them. What else? There's my website, which is garbage, but still has some information on it. Here's me and my cat. Here's the thing I was talking about. Here's a link to where you can make a 30-minute individual appointment with me. So if you're like, hey, James, I don't really love the office hours because there's tons of people in there, which there sometimes are, sometimes aren't. You can make a one-on-one appointment where you can even say you and another student can do it together. And you can click on this and it'll take you to Calendly, and then you can pick a time somewhere on here. It's been a while since I looked at this. No times in March, sure. I guess I don't have any times tomorrow. Are there no times in April? Okay, yeah, there's time. So apparently I'm not available on Wednesday, but other days of the week I have availability. Let's take a look. Okay, there's not a lot of it. Okay, I have to. I don't have a ton of availability, but there is some availability. So if you're looking for a one-on-one appointment, I usually don't get a lot of requests for those, which is probably why I don't have a lot of availability. But if you would like to do that, I'm here. What else is on my website? Links to my Zoom classes, links to my office hours. Yeah, not a lot. Not nearly as great as Grant's wonderful website of resources. Okay, that's syllabus. There's Morris's Canvas. I think that's about it as far as this first page. Let's talk about the rest of the stuff. We'll skip the modules for now. We'll do modules last, because that's kind of like where most of the stuff is. Let's look at the assignment section real quick. Here's where you see the reflections and the quizzes. The reflections are pretty much just each week I'm going to have you guys in Canvas. You'll just do the thing. You'll type stuff. I'll have you every week give me a very brief 1 to 2 sentences, bullet points, summary of what you covered in your Math 21V class on Monday, Wednesday, and Friday. Really just like give me the highlights. But it's a good opportunity for you to think about what you actually did last week. A math question. This can be from your homework, something that came from the class, something from a handout, something from a quiz I gave you, really anything that pertains to the class. And I will say, you can ask it in the reflection in Canvas, or you can write it in a discussion and be like, hey, James, I'd ask my question in the discussion. So discussions, use it. Okay. Always optional and appreciated. Jokes, memes, send my way. My other classes have all, not everybody always sends me jokes and memes, but a good portion of the students do. It brightens my day. So it is optional and it's very appreciated. Not optional. Okay, not optional, but it's totally optional if you don't want to answer any questions about yourself. I would like to try and get to know you guys somehow, some way. So this is what I've come up with. Every week there'll be various questions about yourself, and usually I write stuff about myself too, like not on this one, but let's look at the next one. I think like 3, 4, shut the door. Yeah, so like here, what's your major? I talk about how my major was math, but I started in aeronautical science and engineering because I thought I wanted to work for NASA, and I'd watched Apollo 13. Anyway, so those are the reflections, really just typing stuff, telling me about yourself, telling me what you've done in your class, asking me math questions. Those are weekly, so they usually become available. I think that's April 5th is they become available April 1st, which is Thursday, and they're due this first one's available the 1st, which is a Thursday, and they're all available on a Thursday. This one's due April 5th, which is a Monday. So they become open Thursday, due Monday. So you might do it over the weekend. And then the quizzes, similar as far as when they are available and due. Yeah. So available Thursday, due Monday. Quiz number 1. So when you click on the quiz, oh, there is a quiz there. I wonder if this quiz, let's check this quiz out. I might need to update it. Yeah, I will think about if this quiz is really what I want to have you guys do this week or not. But the whole idea is the quiz will be here as a PDF. You can look at it, you can download it, whatever. Answer the quiz questions. Either you can write on this with a tablet, you can print it out if you really want to. I don't need you to print it out, but you can. Or you can just write your answers on a blank piece of paper, scan them using whatever scanning device you want, and then upload them to Gradescope. So you will go to Gradescope, and right now you won't see the quiz because I haven't put it in Gradescope yet. But if I've linked the assignment, which I intend to do, then you can, it'll take you right there, and then you can scan and upload your assignment. Do make sure you scan and upload a PDF, not pictures. It does make it a little easier to deal with. Yeah, I think that's it as far as that goes. Sure. And then there's the attendance down here. That way I will mark the attendance. You don't need to keep track of it. But if you believe that I have misrepresented, that's not really what I would say. If I haven't correctly marked your attendance, please let me know and I will fix it. Zoom, I don't want to go look at the Zoom records to see who was here, but I can. Sometimes I do that, like if I forget to take a screenshot of everybody that's here, which I'm actually going to do right now. I'm take a big old screenshot of everyone that's here. That's actually the easiest way for me to then go enter the attendance later. But if I missed you somehow, I can go check the Zoom attendance record to see if you were here. And I will definitely do that if you tell me that you were here and I forgot to mark you here. Okay, discussions, announcements. Sometimes I write stuff in announcements like, hey, the quiz is available, or hey, you should do this thing. Files, there's some files. I think these are all my old quizzes from couple quarter, I think from fall quarter, when I talked about 21B. Pages, I don't think there's any pages. Oh no, oh, that's right. So you guys have kind of some extra stuff because I taught code 21B relatively recently in fall. So let's look at the modules. This first module here, you won't be able to see. It'll become live May 24th. It's just to take the evaluation of our class. Course information, I could post something there, maybe. I don't think, I think we're pretty good. If you have questions though, right, I feel like we're good, but I don't know. I'm not the student, so I don't know what I might be missing to say. But then we go down here and we have some useful handouts. So let me do this. I still want these things open, but so we got some useful handouts, which some of them you won't use just yet, but like this first one is a list of like all the antiderivatives, which I know she also talked about in class. Well, I should, right. So it's on the left side, here's your derivatives. On the right side here are your antiderivatives that go along with the same derivative rule. I don't love this K notation, but it is pertinent, so we can use it. We'll talk actually about that today because it is kind of worth knowing that the antiderivative of like e to the 4x is 1/4 e to the 4x and so on and so on. There's a fundamental theorem of calculus handout, which you might want to look at after you guys have talked about the fundamental theorem of calculus. There is a handout on inverse trig stuff. Yeah, in fact, yeah, okay. So Daniel, we will definitely make sure we talk about all the derivatives. So in fact, let me go back to that previous list here. So I can definitely talk about any derivative on this list. She said there were 12 rules, and there are, I guess, technically, if you're in Schulten's class. But we can talk about any and all of them. I can definitely run through them pretty quickly. I imagine some of you might be missing the inverse trig ones, which I'm happy to cover. They're not too terrible. Yeah, we'll get there. Maybe that's what we'll start with once I very shortly here finish talking about what else is in the modules. So there's this inverse trig stuff, which again, this just says what the antiderivatives are. It doesn't actually say how to find them. It's all right. We'll talk about that as well. And then I have some, I have another, all right, it's got lots of handouts. Some of them sometimes they're kind of repetitive. Here are some derivatives to know. Yeah, so there's lots of good handouts. And then there's this last one, which we will definitely use once we start talking about integration techniques. This is kind of a, for lack of a better word, a flow chart of how to determine what method of integration you should try to use. So like, yeah, and we'll get into that. I don't really want to get into it now because it's pretty lengthy, right? There's a lot of stuff to kind of cover here about what should I do if I have this kind of thing. Yeah. Okay. There's some old practice exams. It looks like these are all specifically exam 2 practice exams. So I will find some exam 1 practice exams. And then you guys won't be able to see the quizzes and quiz solutions. But then if you go down to the bottom, there's literally all of my recordings from the last fall quarter. So if you're wanting to see something that either I haven't talked about yet, or maybe you want to see a different version of it, I mean, a lot of these will probably be pretty similar to what we do this quarter, but not exactly the same. So if you're looking for stuff, I've labeled most of them with, what they kind of are about. So if you are looking for more video stuff, they are lengthy. They're all like an hour and plus long, but you can definitely look through them. And then we also have the problem solving sheets. These are the same or very similar to the sheets on Grant's website. So if you're looking here or looking at Grant's, it's pretty much the same stuff. And then there's also this link to video lessons by math specialists. You go over there and then you go, and it does take you straight to 21B. If you scroll down, there's a lot of, there should be a lot of, yeah, okay. There's a lot of short videos by me and Sarah and Grant. These are all definitely from when we were kind of first doing all the online teaching. So they might feel a little dated, but they definitely, there's lots of good stuff here. So if you're looking for more resources and more examples of stuff, these are, I had a beard there. Oh yeah, look at all that beardiness. These are some good places to watch not super long videos of stuff. Yeah. Okay. So before we get to the math, are there any questions about just kind of how the class works? I'm going to stop sharing my screen. All right. So it's like wait, so you guys have a chance to ask questions, but I feel like I waited. You're always welcome to ask questions. Really, like that's kind of, I mean, I wouldn't say it's my mantra, but it's definitely my ethos, I suppose, right? Ask questions. I will try my best to answer them or guide you to how to figure out the answer. Yeah. So let us talk about all the derivatives and all the antiderivatives that you need to know. You shouldn't, I don't think there's any expectation currently. When will the quiz be unlocked? Thursday. And again, you definitely shouldn't stress about the quiz. Like this quiz, 1, is not meant to be super hard. 2, I mean, so I should say it's not meant to be super hard, but it might be hard. 2, as long as you write something, you will get credit. The whole point of the quiz really is to give you an opportunity to try something, have it graded so that you can get feedback about it. But as long as you do it, you'll get full credit. But yeah, it'll be unlocked Thursday because really I need to write it because I don't know if what I've got up there is really what I want or not. It's my older quiz, so yeah. But I was saying, as far as Daniel's comment, you really, the only expectation, well, that's not true. It should be that the only expectation that you know for antiderivatives that you know are things you already know their derivatives. So for example, if you know the derivative of x squared is 2x, you also know the antiderivative of 2x is x squared. So let's start there actually. So yeah. Oh, I should pin my, so I do need to pin my video. Yeah, now they're going to get more complicated, but yes, you're totally right. So the thing that gets actually challenging about finding antiderivatives is when they're not just ones that we know off kind of the top of our head. So let me do just a couple things here. Don't want you, yeah, I want you, go away. Sorry, I just got a bajillion things open here. Okay. So, can we write questions on this quiz? Something like yeah, totally. That's totally fine. Yes. Yeah. You can totally write like, I don't know, this problem. And that would be perfectly fine. All right, let's see. So the only thing I don't love about where my computer is like when I stand here, which is where I usually stand, you don't see like my eyes, which is kind of a bummer. I mean, it's just weird for me. I guess that kind of works. That might be better. We'll see. All right. So here's kind of what I want you, what I want you guys to know. Really, so there's some notation stuff. First of all, so often people use lowercase letters, lowercase functions for the function. So let's say our function was 2x, and they use uppercase letters for the antiderivative. So the antiderivative of 2x could be x squared, or it could be x squared plus 5, or it could be x squared plus 1,000,000, or it could be x squared plus pi, or it could be x squared plus e. It could be x squared plus any constant, or minus, right? It could be x squared minus 5, which you'd say is plus -5. So here's the idea. If you go this way to this way, you're differentiating, right? From here to here, you're taking the derivative. So the derivative of x squared equals 2x. And going this way, you're taking the antiderivative. The antiderivative of 2x is x squared plus c. The whole point of drawing this very simple picture is that I want you to notice the relationship between these two things. They undo each other, right? If you do the derivative of something and then the antiderivative, you end up essentially back where you started, right? You might have a different constant, right? If you take the derivative of x squared plus 5, you get 2x, and then the antiderivative of 2x could be x squared plus 7. But if you ignore the constant, taking the derivative and then the antiderivative, you get back where you started. The same thing is true if you go the other way. If you first take the antiderivative and then take the derivative, you get back where you started. So these are what I like to think of as inverse operations, or operations that undo each other. And that's really kind of a big deal. And that's some of the main essence of what this whole quarter of calculus is about, is that anti-differentiation and differentiation undo each other, hence the names. So essentially, right, we're asking the question, if my function is something like, I don't know, x to the 5th, and I want to know what, my 5's never really good, sorry. My function is x to the 5th, and I want to know what's the antiderivative. So when I'm asking for the antiderivative, I'm really asking for, okay, well, what's the function that if I took the derivative of it, right? What I'm really asking is, what function, we're going to call it capital F of x, has a derivative that is x to the 6th, x to the 5th. Okay, well, I know that when I take a derivative of x to a power, the power gets 1 less. So I need the power to be 1 more to counteract that. So I'm thinking that my antiderivative here is probably something like x to the 6th. But that's not quite right. If we take the derivative of x to the 6th, what do we get? We get 6x to the 5th. But I want just x to the 5th. Luckily, the constant multiple rule tells us that we can multiply by anything and not really change what's happening, meaning I can totally multiply by 1/6 And the derivative of 1/6 x to the 6th is going to be 1/6 times 6x to the 5th, which is just going to be x to the 5th. And yeah, I need a plus c. So we can write this as 1/6 x to the 6th plus c, or equally good, x to the 6th divided by 6 plus c. That's how I usually write it, but either way is perfectly fine. And that's the what I usually call the anti-power rule, right? It's the power rule, but it's the antiderivative version of power rule. So this is right. This is just the very basic, like antiderivatives and derivatives undo each other. When you're trying to find an antiderivative, you're trying to find the thing that if you took the derivative of that thing, you would get back the function you started with. So the antiderivative needs to undo what the derivative would do. Okay. So let's talk about all the functions that we should be able to differentiate and anti-differentiate. And I should probably, I wrote down some stuff here. Yeah. Okay. So some difference. Yeah. Okay. Whatever. So the rules we need to really kind of be aware of right now are not the sum or difference rule, although they kind of, they'll come into play, or the product or the quotient of the chain rule. It's really kind of the, well, yeah, I mean, the list there. Let's just talk about what kinds of functions we know how to differentiate. So we know how to find the derivative of, say, and this is my kind of preferred notation for the derivative. I will also point out, just because I was looking at the assignments, it looks like in Schulten's, in fact, let me just show you guys. Oh, no, they both, yeah. Yeah, let me show everybody real. I mean, I'm sure you can see this on your own, but let me just point out that in both of these assignments, Schulten's, most of them, the variable is x, but occasionally there's like everything's in terms of y or in terms of t or in terms of s. That's just the variable you're using for those problems. For Morris, I feel like there's more of them that are that way, like s, t, u. I don't know. It's about it's pretty similar. So the assignments do look similar. I would say Morris's looks a little bit longer. So just be aware, right? Sometimes people use different variables. That's perfectly fine. If I want to take the derivative, you know, like x to the nth power, it's going to be equal to n times x to the n minus 1. And she was talking about how this is. I watched Schulten's class. I didn't watch Morris's class. So Schulten's was talking about how this is true for integer values of n. It's actually true for any value of n. And then on the flip side, and so I am just going to start using this in antiderivative notation because it's easier. I don't want to write the words the antiderivative of whatever is equal to whatever. So we're going to use this notation, the antiderivative, and this does have other meaning as well that we will talk about when we get there, which will not be too far away. The antiderivative of x to the nth power with respect to x is equal to x to the n plus 1 divided by n plus 1. That's a rule we have. Plus c, of course. Now, this rule does have one caveat. Doesn't work for n equal to -1. So it does work for any other power of n, meaning if I want to find, say, I'll use two different notations here. If I want to find the antiderivative of, say, x to the 3rd plus the square root of x minus 1 over x to the 9th, well, before I can find the antiderivative, I need to rewrite it. So they're all nice powers of x. So I'm going to rewrite this as f of x equal to x to the 3rd plus x to the 1/2 minus x to the -9th. It does need to be, so if you're talking about anti-differentiating or differentiating powers of x, they'll have to live in the numerator, right? It would be very, right, so just as a quick aside here, right? If you want to take the derivative of 1 over x to the 9th, it's not equal to 1 over 9x to the 8th, right? It's equal to the derivative of x to the -9th, which is -9x to the -10th, using the power rule. So whenever you're differentiating or anti-differentiating powers of x, they need to literally be just in the numerator and not anywhere else, not the denominator. Okay. So then if we want to anti-differentiate this, the antiderivative is going to be, so we're just going to use the reverse power rule or the anti-power rule. We're going to add 1 to the power and divide by the new power. So we're going to get x to the fourth divided by 4 plus x to the, okay, 1/2 plus 1 is 3/2. And dividing by 3/2 is the same as multiplying by the reciprocal 2/3. So we often kind of do that all at once. And then -9 plus 1 is -8 divided by -8. And I would probably make this minus minus a plus. But that would be our answer. I will point out in this example, we totally use the sum and difference rule without even thinking about it, right? We use the fact that the antiderivative of a sum and difference of 3 different functions is just the sum and difference of those 3 different antiderivatives. So as far as the sum and difference rules for derivatives and antiderivatives are concerned, you shouldn't think about them because we never think about them. We just use them. Right? If you're differentiating a bunch of things added or subtracted together, or anti-differentiating a bunch of things added or subtracted together, you're just differentiating or anti-differentiating as appropriate, and then adding or subtracting all the results together. Let's do the same sort of thing for, yeah, we can do it here. Let's do the antiderivative again. So I'm just going to start using this notation. This notation just means, right, find the antiderivative of whatever is between the integral symbol and the dx. Again, I do know that that symbol carries other weight, and we will definitely talk about that more when we get there. But it is the notation we use for antiderivatives, so it's really convenient. This is also called the indefinite integral, but it means finding the most general antiderivative. Slap on that plus c. Okay, let's do another example, a little bit more challenging. I don't like that, sure. Let's do fun times. Why not? X, what do I want here? Sorry, x cubed plus the square root of x plus the cube root of x, all divided by x. So again, we can't just say it's the antiderivative of each part and throw it all in one box. We have to simplify things. And this is generally true. We often need to simplify stuff before we can anti-differentiate it or differentiate. And we're still going to be differentiating things. So I'm going to divide each thing by x. This is a very common tactic when you have an integral of some quotient where everything is powers of x. I'm going to write this as x cubed divided by x plus x to the 1/2 divided by x plus x to the 1/3 divided by x dx. Now forget the little dx there, it is kind of important. And then I'm going to simplify each of these. Right? This is going to be the antiderivative of, let's see, x cubed divided by x is x squared. X to the 1/2 divided by x to the first, we subtract the powers, and 1/2 minus 1 is -1/2. So you get x to the -1/2. And the same deal here, 1/3 minus 1 is -2/3. So we have x to the -2/3. Now we're actually ready to anti-differentiate. So again, we're just using the same anti-power rule. We're adding 1 to the power, dividing by the new power. So we're going to get x to the 3rd divided by 3 plus x to the -1/2 plus 1 is +1/2 divided by 1/2. And then x to the -2/3 plus 1 is +1/3 divided by 1/3. And then plus c. And then you should simplify this. You should write this as x to the 3rd over 3 plus 2x to the 1/2 plus 3x to the 1/3 plus c. So anti-power rule is what it is. The reason it doesn't work for -1 is because, right, if n was -1, you would be dividing by 0 in this process. So can't do that. Let's talk about some other derivatives, though. So there's a bunch of derivatives we should know. And if you have questions about them, please stop me along the way. So of course, there's all the trig derivatives. Let's write them all down, right? It's good to remember them. So here's what we got. We've got the derivative of sine of x is equal to cosine of x. There's kind of actually, let me write down, so there's a pattern to this that I think you all should know. And the pattern is we typically do sine, cosine, tangent. So cosine is negative sine of x. Derivative of tangent of x is secant squared of x. And then we do the reciprocal functions over here. So the reciprocal of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of tangent is cotangent. And this is kind of the standard order that we write the 6 trig functions in. But there's a nice little pattern. And it's that basically functions and their co-functions kind of have the same derivative. Here's what I mean. Tangent and cotangent are co-functions. Secant and cosecant are co-functions. Sine and cosine are co-functions. The derivative of sine is cosine. The derivative of cosine is cosine, which is sine, but with a negative. So basically, whenever you, like the co is kind of like an on-off switch. So basically, you can just add a co onto both of these, and the co of sine is cosine, and the co of cosine is sine, but it's negative. The other part of this pattern is that every co-function, cosine, cosecant, cotangent, is going to have a negative derivative. That's really nice. Makes it easy to remember what's what. Okay, so the derivative of tangent is secant squared. The derivative of cotangent is cosecant squared, but negative. The same pattern works for secant and cosecant. The derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x is cosecant of x times cotangent of x, but negative. There's your 6 trig derivatives. Definitely need to know these. There they are. But I should point out now that we know the 6 trig derivatives, we also know some antiderivatives, right? We know that the antiderivative of cosine of x is sine of x. I should start with, fine. Now I should be a little more specific here. So you could say the antiderivative of negative sine is equal to positive cosine, but we almost never write it that way. Wow, that's the x, sorry, let's see. What we instead say is that the antiderivative of sine of x is equal to negative cosine of x. It's always perfectly fine to multiply both sides by any constant you want, because constant multiples don't affect what your antiderivative is. That's the constant multiple rule, right? If you take the antiderivative of a constant times a thing, right? Like if you take the, just as kind of a, let me go back to the side for a second. Sure, I meant to, I knew something. If you wanted to find, say, like the antiderivative of 6x to the 8th, well, it's going to be 6x to the 9th over 9. What we're really doing there is we're kind of ignoring the 6, and we're saying, oh, I know the derivative of x to the 8th is x to the 9th over 9. So I'm getting 6 times x to the 9th over 9. So when you have a constant multiple, it just, as I like to say, just hangs out. So, and the -1 is a constant multiple. It can just hang out. We can multiply this by the -1. The antiderivative of cosine of x is sine of x. Right? Literally, I'm just looking at these rules and undoing them. The antiderivative of secant squared of x is tangent of x plus c. The antiderivative of cosecant squared of x dx is negative cotangent of x plus c. The antiderivative of secant x tangent x is secant x plus c. The antiderivative of cosecant x cotangent x dx is negative cosecant x plus c. So these are all antiderivatives that you're expected to know because you know these derivatives, right? If you know that the derivative of secant is secant times tangent, then you automatically have the knowledge that the antiderivative of secant tangent is equal to secant plus c. So that's what I mean by like these derivatives and antiderivatives undo each other. If you know a derivative, you also know the corresponding antiderivative. Now I will point out, nowhere on this list do we have a thing whose derivative is equal to secant or tangent or cosecant or cotangent. Those are antiderivatives we will learn eventually. Like we will definitely know someday what the antiderivative of tangent is or the antiderivative of secant is, but not today. They require other methods of integration. Okay, so trig derivatives and antiderivatives. Let's talk about a few other things. And then we'll talk about kind of the more complicated version of things after we get through all these. So we definitely know that the derivative of e to the x is equal to e to the x. Awesome, best one ever, right? How would be the best way to memorize them? Good question, Daniel. So I would memorize the derivatives personally, right? So again, my point kind of intends to be that if you can remember the derivatives, then you should be able to remember the antiderivatives because they're kind of the same. But I definitely remember, so the way I remember it is, I remember you just kind of have to remember sine and cosine, right? Get them in there. Derivative sine is cosine, derivative cosine is negative sine. I remember that all of the co-functions, literally the word starts with the letter CO. It's a co-trig function. All the co-functions have negative derivatives. And then you have, so I specifically remember these two. I remember tangent and secant. Your tangent is secant squared, and then I automatically know the derivative of cotangent is negative cosecant squared. I'm literally just appending on a co and a co to get there. Same deal here. If you can memorize this one, your secant x is secant x tangent x. If you put a co in front of everything, and remember that you need a negative, your cosecant x is cosecant x cotangent x with a negative in front. So that's how I remember them. What I've told people to do in the past when we were in more normal times was to write them down on a piece of paper and make it the background of your phone. I've not done that for this, but when I was teaching another class and there was something I just couldn't remember, there was like a whole list of things I was trying to remember, I made it the background of my phone. It really helped me kind of, that's how that works. Yeah, so that's something you can do even now. I mean, right, we look at our phones all the damn time. So maybe that would be a good way to get these particularly in your head. Okay, so the derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x plus c. That's a c. Okay, slightly more challenging, and I feel like this one we might need to talk about. The derivative of a to the x. So she kind of just went through this one quickly in class. She said it was a to the x times the natural log of a. Would anyone like to see where this comes from? I see a raised hand. Go ahead. Is that Ulysses? Go ahead, Ulysses.
Oh, yeah. I was just wondering if we could see where it comes from. Yeah.
Yeah. In general, if I ask you guys if you want to see where something comes from, if anyone types yes in the chat, we're going for it. So type yes, say yes, we'll do it. Even if no one says yes, I'll probably still do it most of the time. So there's actually two ways to see this. Let me show you both ways. And let me pick a real number instead of a. So let's say I want to find the derivative of 2 to the x. So one way, which I actually hadn't really seen until a couple quarters ago, is to write 2 to the x as, so notice I'm writing the derivative symbol every time, right? Because I still am telling myself I need to take the derivative. I haven't taken the derivative yet. I'm just rewriting 2 to the x as e to the natural log of 2 to the x. This is kind of a weird way, in my opinion, a weird to me way of doing it. Okay, and now I'm going to use my logarithm rules. Say, oh, I got the natural log of 2 to the something. I can bring down that x in front of the natural log. So I can rewrite this as the derivative of e to the x times the natural log of 2. Okay, quick aside here. Everybody should be able to tell me, what's the derivative of e to the 6x? It's e to the 6x times what?
It would be times 6 because you're taking the derivative of 6x.
Exactly. The same thing applies here, because natural log of 2 is also just a constant. It's a less nice constant, right? It's not 6, it's like 0.69 something, but it is a constant. And so when I take the derivative of e to the x times natural log of 2, I get e to the x times natural log of 2 times the derivative of x times natural log of 2, which is the constant natural log of 2. Okay, but I don't want to leave my answer looking this way. And I will point out that 2 to the x is the same as e to the natural log of 2 to the x is the same as e to the x times natural log of 2. So that this part here, this e to the x times natural log of 2 really is just 2 to the x times natural log of 2. So when you take the derivative of some base to the x power, some exponential function, the derivative is always that same exponential function times the natural log of the base. In fact, it's even true right there. It's just that the natural log of e is 1, so we don't write it. Oh, wow. I usually don't hear the ink in my pen. It's like, that's weird. Okay, I've never noticed that before, that the ink was so fluid. I guess it would be. All right, so the derivative of a to the x is a to the x times natural log of a. There is another way of showing it to you guys, well, no, you definitely know it's worth your while because it's going to come up again when we talk about the derivatives of the inverse trig functions. So let me show you the other way of doing this. Start with y equal to 2 to the x. Take the natural log of both sides. Natural log of y equals the natural log of 2 to the x. Bring the x down in front. So the natural log of y equals x times natural log of 2. Take the derivative of both sides. We're assuming, and it's true, that y is a function of x. So when we take the derivative of this side, we're going to use implicit differentiation and say, okay, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. It's just the chain rule, right? If I was taking the derivative of the natural log of x cubed plus 1, the derivative would be 1 over x cubed plus 1 times 3x squared. Same deal. It's 1 over the stuff times the derivative of the stuff. On the right-hand side, the derivative of x times a constant is 1 times the constant. Solve for y prime. Y prime is y times natural log of 2, but y is 2 to the x. So y prime is 2 to the x times natural log of 2. Same over here. So two different ways of getting there. They both get you there, though. But long story short, the derivative of an exponential function with the base, with any base really, is just that same exponential function times the natural log of that base. Okay. Yeah. So then that leads us to the kind of the follow-up question is, well, what's the antiderivative? I think I'm gonna erase this one over here. It's one of the biggest downfalls of teaching from home is the very, very limited board space. Okay. So here's something I really, really, really want you all to take to heart. If taking the derivative of something would make you multiply by a constant because of the chain rule, or because of really any rule, but mostly it's because of the chain rule. So let me repeat that again. If taking the derivative makes you multiply by a constant, which this process certainly does, then the antiderivative will make you divide by that same constant. There's actually a couple ways we can see it here. So I will just point out that the antiderivative of 2 to the x is equal to 2 to the x divided by the natural log of 2. And more generally, the antiderivative of a to the x is equal to a to the x divided by the natural log of a w plus c. And there's a couple ways to see this. You can either say, well, hey, I'm just going to take, so one way you can check if your antiderivative is correct is taking the derivative of this and getting back to where you started, because the derivative of the antiderivative should be equal to the function you started with. Well, let's take a look. Let's find the derivative of 2 to the x divided by the natural log of 2. It seems kind of silly to write the plus c, because we know the derivative of the plus c is going to be 0. That's fine. Okay, now we're not going to be foolish here. We're not going to use the quotient rule. We could. It seems silly though when the bottom is a constant. Instead, we're going to rewrite this as the derivative of this constant multiple, 1 over natural log of 2 times 2 to the x plus c. And now take a look. I've got the derivative of a constant times a function. When you take the derivative of a constant times a function, the constant hangs out, and we take the derivative of that function. The derivative of 2 to the x is, I erased it, but it's 2 to the x times the natural log of 2. But hey, look, the 1 over natural log of 2 times the natural log of 2 cancels out. And you get 2 to the x, which is what we wanted, right? If this is supposed to be the antiderivative of 2 to the x, then the derivative of this should equal 2 to the x, which it does. Yeah. There's another way of imagining it, but I think this is probably perfectly good. Okay, so let me see what else is on my list here. Oh yeah, we need to get, so we've got logs and we've got inverse trig functions, and I think we've pretty much covered all of the functions you're supposed to know how to differentiate or anti-differentiate, which I think is a good place to start. Yeah, but actually, so before I get to the logs and the inverse trig, I want to kind of harp a little more on that point I was making, that if your derivative would make you multiply by a constant, your antiderivative makes you divide by that constant. And let me see one thing here. How did they write that? Okay, sure. Yeah. So let's say I wanted to find the antiderivative of secant squared of 4x. Okay, here's what I know. So I don't really want to differentiate this because, okay, derivative secant squared, you have to use the chain rule a couple times. But I know like at the last step of the chain rule, I'm going to be multiplying by the derivative of 4x, which is 4. And so that I know that basically I'm going to have to divide by 4 to counteract the 4 I would have to multiply by. So I know the antiderivative of secant squared of x is tangent of x. So the antiderivative of secant squared of 4x is tangent of 4x, mostly. But I know that's not right, because I know, and you know, that the derivative of this, I suppose a better way to say it is, if the derivative of your answer is going to make you multiply by a constant, you probably have to divide by that constant. right? You take the derivative of this, the derivative of this is secant squared of 4x times 4. I don't have a times 4 over here. So I need either a 1/4, if you prefer, or division by 4. It's the same deal. Doesn't matter which way you write it. But when you antidifferentiate something where you have a constant multiple of x, we have to divide by that constant multiple. Same deal for something like, sine of 3x. I know the antiderivative sign is negative cosine. So it's going to be negative cosine of 3x. But if I look at this, I can see that if I take the derivative, I'm going to get multiplication by 3 because of the chain rule. So I have to divide by 3 to counteract that. So these are all those k's, right? In her list of like, and again, I'm referring mostly to Schulten's because I've only walked through stuff. Like when you have like the rule, like the antiderivative of, let's pick a different one, secant of kx tangent of kx dx. Well, I know that the antiderivative of secant of x tangent of x is secant of x. So this is going to be secant of kx. But again, here's the problem. If we take the derivative of this and use the chain rule, which we have to do, the derivative of secant of some stuff is secant of your stuff, tangent of your stuff, times the derivative of the stuff. But the derivative of k times x is just k. So the derivative of this has an extra multiple of k. I don't want that. So eventually we end up kind of getting very, very used to the fact that if your thing that you're antidifferentiating specifically has a constant multiple of x, we have to divide by its derivative, which is just divide by the constant. I really, really, really need to stress it is only true when you have constant multiples of x. It does not work if you try and do something like this. If you want to do like the integral of sine of x squared, which actually is impossible, this cannot be antidifferentiated, but it will tell you it's definitely not equal to negative cosine of x squared divided by 2x. Right? It's not the same thing at all. Because here, right here, since you're dividing by something that's not a constant, you'd have to use the quotient rule to differentiate this. So it's a totally, totally different process. So it works for constant multiples, does not work for anything else. Okay, let's get to the logs and the inverse trades. We need a break. Let's take like a 3-minute bathroom break. I'm gonna get some more water. I'll come back in 3 minutes. Yeah, I'm gonna pause the recording. Remind me when I come back to unpause the recording. Recording in progress. Great. So we're gonna do derivatives of logarithms and then inverse trade. And I think we should be pretty well covered. Yeah, that should be all right. Okay. So the derivative of the natural log of x is 1 over x. Or if you prefer, you can also write it as x to the negative 1. So that definitely informs us that the antiderivative of 1 over x, or if you prefer, the antiderivative of x to the negative 1. I will point out, just because this does come up a little bit later and some people find it a little confusing, sometimes people prefer to write this as the antiderivative of dx over x, right? If you have just a 1 in your numerator, sometimes people are like, oh, 1 times dx is dx. So people write this way. I don't usually love it this way, but people do write it that way, so just be aware. Antiderivative of 1 over x is the natural log of the absolute value of x. Now, you might be like, hey, James, those aren't exactly the same. And you're right, they're not. So I feel like there's a little bit of discussion that's warranted here. We'll try and keep it brief. Here is the way I would kind of describe it. When you take the derivative of something, the derivative should have a domain that is at most the same size. So here's what I mean. Let me see if I can think of a good function. Oh yeah, let's talk. So here's what I mean by this. Let's say my function is the square root of x, which is x to the 1/2. The domain of that function is all non-negative numbers, meaning 0 inclusive to infinity. The derivative is 1/2 x to the negative 1/2, which we can write as 1/2 square root of x. And you'll notice here the domain is actually slightly smaller. The domain of the derivative is 0 exclusive to infinity. So what I'm trying to say, maybe a roundabout way, is that when you take a derivative, the domain should either be the same size or smaller. Your domain shouldn't really get larger because the original function should kind of be the entire domain, right? You can't take the derivative of something from 0 to infinity and then say get a function that's defined on a larger domain. Well, that actually kind of happens here, right? The derivative of the natural log of x is 1/x, but the domain of the natural log function is 0 to infinity. But the domain of the 1/x function is everything but 0. So here's the issue, right? When you talk about the derivative of the natural log of x being 1/x, we're actually restricting x to be greater than 0. So graphically, here's the natural log of x function, and here's the 1/x function when x is greater than 0, right? So we don't get this part down here. But the problem is here we're starting with 1/x, and we're kind of working our way backwards. So we're always starting with, well, this function, there isn't any domain restriction, right? 1/x, x can be anything except for 0. So when we need to differentiate it, we also need to have kind of at least that much domain, which the natural log of the absolute value of x does have. And maybe like, well, James, we just can't slap on absolute value of x whenever we want. That's also true. But the thing is, it's also true that this function, the natural log of the absolute value of x, has the same derivative. What do I mean? So natural log of the absolute value of x. So when you take an absolute value of something, you get kind of, well, literally, you get a piecewise function. If x is already positive, then you just get the natural log of x, right? If x is positive, you don't change it. But if x is negative, right? What's the absolute value of, say, -5? Well, it's +5. But how do you change a negative number to a positive? You're like, well, just make the minus sign disappear. No, you multiply it by -1. So you're taking the absolute value of something negative. The way you change it to a positive is by multiplying it by -1. So the natural log of absolute value of x, if x is already negative, it's going to be the natural log of -x. Because then if x is negative, -x is positive, and the natural log of a positive number is perfectly fine. Okay. So then let's take the derivative. So the derivative of the natural log of the absolute value of x is, well, the derivative of the natural log of x is 1/x when x is greater than 0. The derivative of the natural log of -x, we have to use the chain rule, is going to be 1 over your stuff, 1/-x, times the derivative of your stuff, which is, well, the derivative of -x is -1 when x is less than 0. But look, these are the same. 1/-x times -1 is 1/x. So whether x is positive or x is negative, the derivative of the natural log of the absolute value of x is 1/x, as long as x isn't equal to 0. So that's why we get to say that the antiderivative of 1/x is the natural log of the absolute value of x. And it is something you do need to include, at least as far as I know. Your teacher might say, forget it, it's not that important. I doubt that. Graphically, here's what's going on. Here is your good old Here's your natural log of x function. Intersect at 1, 0. And since it's the natural log of the absolute value of x, it also reflects. That should be symmetric. So here's y equal to the natural log of the absolute value of x. And then here's the derivative. And that seems pretty reasonable, right? So again, if this is our function, we see over here the slope of the tangent line is slightly negative. Over here, the values are slightly negative. As we move to the right, the slope of the tangent line gets more negative, the values get more negative. And close to 0, the slope of the tangent lines are super negative, and the values are super negative. Over here on the right-hand side, the slope of the tangent line is super positive, the values are super positive. And then as we move to the right, the values get less positive, or sorry, the slopes of the tangent lines get less positive. And here, as we move to the right, the values get less positive. So that totally is the derivative of that. Okay. So we have the derivative of the natural log of x is 1 over x. The antiderivative of 1 over x is the natural log of the absolute value of x plus c. What if we have a different base? So it's actually very much the same as with the exponentials, except opposite. So you take the derivative of log base 2 of x. There's actually a couple ways to do it. I'm going to kind of show you guys the short way. We can use the change of base formula. Log base 2 of x is the natural log of x divided by the natural log of 2. But we're just dividing by a constant, right? That's the derivative of 1 over natural log of 2 times natural log of x. Constant multiple hangs out, and the derivative of the natural log of x is 1 over x. So we get 1 over x natural log of 2. So check this out. The derivative of the natural log of x is 1 over x. The derivative of log base 2 of x is 1 over x divided by the natural log of 2 as well. So when we differentiated this other thing, we multiplied by, we multiplied by 1 over natural log of 2, or we divided by natural log of 2. Here's the general formula. Yeah, sure. So the derivative of the log base a of x is 1 over x natural log of a. And so I'm going to remind you, the derivative made us multiply by a thing. Multiply by 1 over natural log of a, or it made us divide by natural log of a. So if the derivative makes you multiply something, the antiderivative makes you divide by that same constant. I should say constant, really. So here, since we multiply by 1 over natural log of a, the antiderivative is going to make us divide by that. So we're going to divide by 1 over natural log of a, which means we're going to multiply by natural log of a. So the antiderivative, am I just saying something? I might be actually, sorry, I might have gotten off on a little tangent that's not super correct. It's not that it's not correct, it's just that we don't really consider it, I don't think. Yeah, sorry, I think I got a little ahead of myself there. Let me double check one thing. Yeah, I don't think we worry about that. Yeah, we do not. We do not worry about trying to integrate something that, sorry. It's later on. So later on, once we learn integration by parts, we'll talk about the integral of the natural log of x. And you can also talk about the integral of log base a or log base 2 of x. And that's when you end up multiplying by the natural log of the base. Okay. We're almost there. We've almost gone through all the derivatives you need to know. There's only really 3 left. Technically there's 6, but there's really only 3. The inverse trig function. By the way, this part here, these inverse trig functions, is going to be where it's really nice to have remembered that just like with the regular trig functions, the derivatives of the co-functions are negative. That also holds for these inverse trig functions. So derivative inverse sine. I can derive it if you want, or I can just tell it to you. Here's what it is. It's 1 over the square root of 1 minus x squared. Should I derive it? I don't mind deriving it. I feel like I should. I'm going to derive it. So here's how you get these derivatives. In fact, actually, let me write them all down and then. So derivative of inverse. So here's the nice thing. Derivative inverse cosine of x is the same as the derivative inverse sine, but negative. That makes it really nice. In fact, the same is true for cotangent and tangent. I should say inverse tangent and inverse cotangent. So the derivative of the inverse tangent of x, you can also say the arctangent of x, is 1 over 1 plus x squared. The derivative of the inverse cotangent of x is negative 1 over 1 plus x squared. And last two, the derivative of the inverse secant of x is, it's a little much, it's 1 over the absolute value of x times the square root of x squared minus 1. Sometimes that absolute value isn't there depending on how people define things. And then the derivative of the inverse cosecant of x is negative 1 over the absolute value of x, square root of x squared minus 1. So this is what I mean when you only have to memorize 3 of these. If you know the derivative of the inverse sine, the inverse tangent, and the inverse secant, then you know the rest. If you know inverse sine, you know inverse cosine is just the negative of it. So the inverse cofunctions go together. Inverse sine and inverse cosine, the same virtually. Inverse tangent, inverse cotangent, the same virtually. And inverse secant and inverse cosecant, the same virtually. Again, the only difference is the inverse cofunction is the negative of the derivative of the inverse of the inverse regular function. So you should definitely memorize these. They're gonna come up a lot. Yeah, they're gonna come up a lot. I'll derive one of them and then we can do more if you guys want. But at this point, really, it is, you kind of need to memorize them. I will point out, and this actually is a really pertinent thing to point out. In each of these examples, if you were to replace x with like sine or the same trig function. So just want to mention here. In this derivative, if you were to say if x is equal to sine of theta, if you replace x with sine, right, the same trig function there, you get a trig identity. I'm not going to write the whole thing, but I'm going to point out that specifically 1 minus sine squared of theta is cosine squared of theta. And same deal here, right? If you replace this with cosine, 1 minus cosine squared is sine squared. It also works down here. If you say x is tangent of theta, 1 plus tangent squared of theta is secant squared of theta. Or my favorite trig identity, I tan and get sexy. You can never forget it now. It is buried in your head. 1 plus tangent squared theta equals secant squared theta, or I tan and get sexy. And then lastly, if you replace the x here with secant theta, so if x is secant theta, then secant squared theta minus 1 is equal to tangent squared theta. This is not a coincidence. This is very, very purposely meaningful. And the reason I'm pointing this out to you is because when you talk about integration using trig substitution, this whole idea comes back. So you're really, really, really going to want to notice that, oh, 1 minus x squared goes with x being sine theta. But look, I already knew that because I knew the derivative inverse sine had a 1 minus x squared in it. And 1 plus x squared goes with tangent. But I already knew that because the derivative of arctangent is 1 over 1 plus x squared. And if I see an x squared minus 1, oh, I'm going to pick secant because I know the derivative inverse secant has an x squared minus 1 in it. So remembering these inverse trig derivatives will really, really help you when it comes to knowing how to do trig substitutions. Okay, But I did promise you I would derive at least one of these, and I think it's worthwhile. And then afterwards, I'll ask you guys if you want me to do more of them. So how do we actually find the derivative of, let's do inverse sine. It's a pretty classic example. Well, it's going to be actually, yeah, it's going to be the same way or very similar way we did, the way we did 2 to the x the second time, where we used implicit differentiation. So we're going to say, okay, well, I'm going to let y equal inverse sine of x. But I'm actually going to rewrite this, because if y equals inverse sine of x, and again, maybe I should take a minute to talk about what an inverse trig function really means, right? If I have the inverse sine of x, for example, if I said like, what's the inverse sine of, I don't know, 1/2, you would all hopefully say, oh, James, of course, that's pi over 6, because sine of pi over 6 equals 1/2. So that's what an inverse trig function says. If you tell me what the trig function value should be, the inverse trig function should give you back the angle you took that trig function of to get there. So more generally, inverse sine of x equals theta corresponds to sine of theta equal to x. Or the way I like to read it, when I read the inverse sine of x, the words I actually say in my head are the angle whose sine is equal to x. Oh, inverse sine of 1/2, I'm looking for the angle whose sine is equal to 1/2. Oh, that angle is pi over 6. Sine of pi over 6 is equal to 1/2. So when you're finding the inverse sine of something, you're saying, oh, I want to find the angle. And if I took sine, or whatever the trig function is of that angle, you would get back the value that is your input. It's very much how exponential and logarithmic things are inverse functions, right? If you say 2 to the third equals 8, right? Or 2 to the x equals 8, you're saying, oh, 2 to what power equals 8? Well, that's exactly what the logarithm asks for. Log base 2 of 8 equals x. It's just the difference is, right, how it's written, but they still give you the same information. So here, right, when I say log base 2 of x, log base 2 of 8, I'm saying, oh, 2 to what power equals 8? Well, I can rewrite it this way. Well, same deal here. If I'm saying, right here, I'm really saying, okay, sine of what value equals x? Sine of what value equals x? Or you can just take sine of both sides and say sine of inverse sine is x. So now we're going to differentiate both sides. Again, with the knowledge that y is a function of x. So differentiating sine of y, well, you're a sine of some stuff, is cosine of your stuff times the derivative of the insides. The derivative of x is 1. Now we're going to solve for y prime. Uh-oh. There's still some y's in my answer. I don't want that. So here's where we either use a trig identity or a triangle. Really, they're the same thing. Let me show you what I mean. I definitely recommend using a triangle. So what I mean when I say use a triangle, I mean take the fact that you know that sine of y is equal to x. Say, okay, well, I'm going to modify that just a little bit. Sine of y equals x over 1. But sine is opposite over hypotenuse. So I can draw a triangle where the opposite side is x. I should say I can draw a right triangle. And the hypotenuse is 1. And then I can find this third side using the Pythagorean theorem. So if I call this question mark squared plus x squared equals 1 squared. So question mark squared equals 1, because 1 squared is 1, minus x squared. So our question mark is the square root of 1 minus x squared. But now, oh, sorry, you know what I forgot to do? I forgot to label my angle. Right, that's the angle, because sine of y should be the opposite over the hypotenuse. Now, I want cosine of y. Well, okay, no big deal. Cosine of y is adjacent over hypotenuse, which is the square root of 1 minus x squared over 1. And there's your derivative. Oh. There is something I slightly glossed over, which is the fact that technically there's a plus or minus here. And you think, oh, James, plus or minus, I don't know about that. Well, here's the thing. Sorry. Oh gosh, brain. Oh yeah. So here's the thing. When you're talking about inverse trig functions, they have a restricted range. Yeah. So when you're talking about the inverse sine of y, the inverse sine of y is between negative pi over 2 and pi over 2, which is the first and the fourth quadrant. But in the first and the fourth quadrant, cosine is always positive. So it can't be plus or minus. It has to be just plus because cosine is positive for the first and fourth quadrant. I wouldn't worry about that too much, but it always kind of works out the way we want it to. But I just want you to be aware that there is kind of a little thing there until it works out. The other way you could do this, which I don't like as much, especially because you're going to want to use these triangles when you start doing trig substitutions, you use the identity. You say, oh, sine squared of y plus cosine squared of y equals 1, and then you can solve for cosine. Cosine squared of y equals 1 minus sine squared of y, and then the square root of that is the square root of that. So cosine is equal to the square root of 1 minus sine squared, but sine is y. So when you're getting cosine of y, sorry, sine of y is equal to x, is the square root of 1 minus x squared. So it still works out the same way. All right. So let me ask you guys, would you like me to do another one of these? Okay, oh. No, it is. You do not have to know how to derive them, but you do need to know what they are. Right. So you don't really. So you don't need to know this process, but this triangle thing is kind of something that you will see again. So knowing this part is kind of useful when you have something. Yeah, well, I'll just leave it there. But no, you don't really need to know how to derive these. So you definitely need to know these. And then we also need to know the antiderivatives. But the thing is, if we know these, then we automatically know these the other direction, right? So if I know that, oh, so actually, so here's kind of something that's important. So if I have like the antiderivative of 1 over the square root of 1 minus x squared, it's going to be the inverse sine of x. And if I was taking the antiderivative of the negative 1 over the square root of 1 minus x squared, I would say it's the negative inverse sine of x. We almost never use inverse cosine, inverse cotangent, and inverse cosecant as antiderivatives of these functions. Without fail, we typically use the ones that are associated with the positive part. So if you're integrating or anti-differentiating, I should really say, if you're finding the antiderivative of negative 1 over 1 plus x squared, let's make it negative 5, negative 4 over 1 plus x squared. I'm going to say, and most people are going to say, it's negative 4 inverse tangent of x plus c. It would also be correct to say that it's positive 4 inverse cotangent of x plus c. But everybody says it's this. These functions, although not the same, differ by a constant. So that's why it doesn't really matter which way you write, because they are the same up to a constant. right? Just like inverse sine and inverse cosine are really the same function up to a constant. So that is kind of our list of the entire set of derivatives, and I guess I should throw in the last one here, right? So the antiderivative of 1 over x times the square root of x squared minus 1 dx is equal to the inverse secant of x plus c. There's probably some absolute values in there somewhere. I feel like it gets a little bit funky. Let me see. Yeah, I think there's an absolute value here. I wouldn't stress too much about this, but just be aware. Yeah. This is kind of, there's some very kind of subtle stuff, especially that goes on with inverse secant and inverse cosecant, that you shouldn't worry about, but leads to sometimes there being an absolute value, sometimes not, depending on how people have decided to define things. But again, don't worry too much about that. Other questions? So I think the thing I want to come back to in the last few minutes we have here is, yeah, I would say definitely take the time. Like if you, I know it does sound super exciting, but like, right, make some flashcards maybe. Flashcards are great. Like I know they're kind of boring, but you might be sitting down somewhere, maybe watching some TV, as one does on occasion, and be like, okay, boom, flashcard. What's the derivative of inverse sine? It's 1 over square root, and then you check, right? That's one way to do it. It does work. I literally used flashcards when I was taking math classes, and it definitely helped me memorize things. So if you've got something you need to memorize, you for sure need to work out a way to make it happen. Certainly on this first homework assignment, there are questions about each of those antiderivatives with all those inverse trig functions. So I believe your teachers do expect you to know these things. They will come up as we go on. I will say mostly the inverse secant ones don't come up, but inverse sine and inverse tangent especially do come up. So yeah. But what I want to say is, I think it's, of all the things I've said today, probably the most important thing moving forward is knowing how to deal with something like this. Sure, let's say how to take the antiderivative of cosecant squared of 6x. Well, I know the antiderivative of cosecant squared is negative cotangent, so it's going to be negative cotangent of 6x divided by 6. Or how to take the antiderivative of, what else have I got here? Let's do a fun one. Let's say it's e to the 1/4 x plus secant of 2x tangent of 2x dx. Okay, so the antiderivative of e to the 1/4 x is going to be e to the 1/4 x divided by 1/4, which is multiplied by 4. And then the antiderivative secant of 2x times tangent of 2x is secant of 2x divided by 2. And then I will point out that the formulas that are given for the inverse trig, or for the antiderivatives that end up being inverse trig, are a little bit weird. Like they're written in this, like for example, one of them is that 1 over the square root of 1 minus k squared x squared dx is equal to 1 over k inverse sine of kx. Let's see. And that's almost never how you're going to encounter it. Very rarely is anyone going to ask you what's the integral or the antiderivative of the square root of 1 minus 9x squared? Yes, it is true that it's equal to 1/3 inverse sine of 3x plus c. But the more typical question is what's the antiderivative of 1 over the square root of 9 minus x squared? And that requires a little bit different work. It actually requires, yeah, it kind of requires a u substitute. I can show you how to do it. Yeah, let's go ahead and do it. So I'm going to factor out a 9 for instance. Let me give myself a little more room here. I'm going to factor out a 9 because the idea is you really want 1 minus something squared. So I factor out a 9, but then the square root of 9 is 3. So this is going to come out as 1/3 integral of 1 over the square root of 1 minus x squared over 9 is 1/3 x quantity squared. And now I guess we could actually use the formula. Right? The integral of 1 over the square root of 1 minus k squared x squared is 1 over k inverse sine of kx. This is going to be 1 over k. There's my k value. So 1 over k times the inverse sine of kx. These end up canceling. So we end up getting just the inverse sine of 1, sorry, that's an x, not a k, of 1/3 x. Interesting.